In this video, we will share details about scientific financial systems revolutionary Quble technology that powers the calculation engine inside SFS's Quotient financial analytics application. Qubles present a new paradigm for the application of data science by marrying the complementary powers of the Python and SQL languages. SFS's Quble design provides a programmatic Python toolset that delivers the following major benefits: localized co-located computation within the SQL environment where your data resides, implicit translation of intuitive Python-based data modeling directives to SQL commands, alleviation of in-memory limitations that plague traditional Python tools, elimination of traditional network overhead for migration of data back and forth between Python and SQL sessions, improved security and data governance as the data resides and stays within the user database, abstraction of details management and data staging, automated persistence of calculated results. Qubles provide a major advancement for the concept of localized compute, which seamlessly brings together data science algorithms and data storage technologies in an abstracted, value added paradigm. At its core, a Quble is a Python based wrapper class for a SQL table. This Quble class provides over 800 manipulation and transformation methods to facilitate advanced data modeling operations. Each of these methods translates Python data directives into customized SQL based commands for execution in the underlying SQL environment where the input data is sourced. To accomplish these goals, the Quble design utilizes column based metadata tags for the columns of the underlying SQL data tables. For example, Qubles distinguish between index and value roles for the columns of a data table. These column roles are referred to as key spaces and value spaces, respectively. Keyspace columns serve for qualifying data records and are also used to join keys with other Qubles, while value spaces serve to provide the data values and calculated results. Other column tags, such as time frequency, currency, time basis, and units, serve to guide proper analysis of the data within a Quble. The example here shows historical monthly stock price data, where the dates column indicates a frequency tag of monthly, and the pricing column indicates a currency denomination of US dollars. Since the prices Quble has two key space columns and one value space column, it is referred to as a two-dimensional univariate Quble. For data modeling purposes, the Quble class methods can be used to implement complex data algorithms. This example workflow highlights the Quble's moving average method. In practice, this method will craft and submit a customized SQL query command to apply the moving average calculation against the underlying prices table. This query will then populate a new table, which serves as the basis of a new Quble that is returned to the Python session. Quble associated data tables can also be easily seeded directly from the Python side using common Python data structures such as pandas data frames. We will now walk through an example problem that highlights the power and benefits of the Quble design. Suppose that we wish to perform a stock-based liquidity calculation defined as each stock's monthly dollar volume normalized by the AUM of an investment fund. We can define this liquidity metric using the simplified Python expression. Liquidity equals prices times volume divided by assets under management. In practice, evaluating this expression may involve complex underlying data preparation and integration operations. We will highlight how the Quble architecture automatically manages these details to save significant time and expense. Each term in the liquidity expression reflects a historical data object that we will define as distinct Qubles as shown here. In this example, the prices Quble is indexed on CDAL security identifiers and monthly dates, while the volume data is indexed on LSEG instrument perm IDs and daily dates. Note that the AUM Quble is indexed on monthly dates and the AUM value space column is assigned with a currency metadata tag of euros. Given that the three pieces of content needed for our liquidity expression initially reside in distinct SQL tables, the execution of the liquidity expression ultimately requires that the data in these three SQL tables be joined together to perform the desired calculations. To evaluate the numerator expression, the Quble logic must first reconcile the fact that the prices and volumes table utilize different security identifiers. In this example, the user settings have directed the logic to reindex the prices Quble from CDAL to instrument perm ID. To accomplish this goal, the Quble logic implicitly generates a SQL query that utilizes the underlying security master facility to perform this remapping. This query populates a new SQL table, which is used to instantiate a new temporary Quble of the modified price data now indexed by instrument perm ID. The Quble logic must also reconcile the fact that the prices and volumes tables incorporate inconsistent time frequencies. In our example, the default user settings direct the Quble logic to convert the volume data from a daily to a monthly time frequency for compatibility with the prices Quble. This goal is accomplished with the customized SQL query shown here that utilizes the Quble's underlying calendar table. Since the time basis metadata of the volume data column has been assigned to sum, the resultant monthly version of this volume data will properly reflect the sum of the daily volumes that occurred across the trading days during each month. This query populates a new SQL table that is used to create a temporary Quble of the monthly volume data. Once these conflicts for the numerator items have been resolved, the Quble class will then perform the multiplication step by implicitly creating a temporary join SQL table with the prices and volume value columns to be multiplied for each security and date key pair. The automated customized query that performs this join and subsequent product operation for the numerator subexpression is shown here. The Quble class also implicitly invokes default user controls on how to handle null values encountered during the multiplication operation. A new table for the numerator term is then generated by applying the product of these two values for each record accordingly. The resultant numerator Quble that wraps the new table populated by this query is shown below. Note that the resultant numerator Quble automatically inherits appropriate column metadata tags for the column roles, time frequency, and currency assignments based on the metadata tags from the two Qubles contributing to the numerator expression. To complete the normalized dollar volume expression, the Python interpreter then evaluates the division of the temporary numerator Quble by the AUM Quble. Before this division operation can be performed, the Quble engine will first reconcile the inherent currency conflict between the numerator Quble and the AUM denominator Quble. Here, the AUM denominator Quble is converted from euro-based data values to USD-based values by invoking a resident historical currency translation SQL table that is provided with the Quble infrastructure. The resultant customized currency translation query for the AUM Qubles table is shown here. This query populates a new table for the modified AUM data, and a temporary modified USD denominated AUM Quble is then created by wrapping the newly created table populated by this currency translation query as shown here. After the resolution of this currency conflict, the Quble engine then proceeds with the required join operation to perform the division of the temporary numerator Quble and the modified AUM denominator Quble. The associated customized SQL query to perform the join and division operation is shown here. This query creates a new column of values derived from the division of the dollar volume by the fund size, which is used to populate a new SQL table. The final resultant Quble data object for the normalized dollar volume is then created by wrapping this final table. Note that the Quble logic renders this normalized ratio to be currency-less accordingly. Now that you have seen all the helpful actions that Qubles perform under the covers for this modeling example, let's have a quick look at the simplified Python experience from the data scientist's perspective. In this example, we demonstrated how data scientists can use Qubles to quickly implement data models from the Python command line. Our example necessitated the automated creation and execution of 5 distinct implicit customized SQL queries to properly evaluate this liquidity expression. Note that the Quble technology provides a powerful design that can facilitate and expedite the application of general data science solutions. For the Quble example in this video, we have highlighted a Snowflake-based implementation of the Quble architecture, whereby the Quble engine translates Python data models into Snowflake's native SnowSQL queries and Snowpark commands. The Quble framework can be offered as a programmatic Python data science toolset to the broader Snowflake community to facilitate advanced data modeling on the Snowflake platform. Other SQL language translations are also possible with the Quble design approach. SFS is currently pursuing a patent on this unique and powerful Quble technology. In conclusion, Qubles provide an intuitive, value-added abstraction layer for Python-based data modeling. Qubles deliver the benefits of localized compute through the automated translation of high-level Python directives into customized SQL commands so that the necessary computations are co-located with the underlying data. Qubles save significant time and expense through the automation of tedious, time-consuming, and distracting data preparation and data management activities. Qubles also foster improved model integrity by avoiding manual detail oversights. Qubles are a new paradigm for modern data science. Reach out to Scientific Financial Systems to learn more about how our revolutionary Quble innovation can accelerate your data science solutions.